system of linear equations is called what if it can be written as AX equals 0? Homogeneous. And AX equals 0, the homogeneous equation, it always has x equals 0 as a solution. What do we call that solution? Trivial. Yeah. A non-trivial solution to AX equals 0 has to have at least one free variable in it. True or false? True. Okay, so today we're going to learn how to express the general solution of a linear system using something called parametric vector form. You already know how to solve it, and we already know one way of writing the solution down. We're just going to learn a new way of expressing the solution. And then we're also going to see the relationship between the solution to a non-homogeneous system and its associated homogeneous system. And we'll practice describing sets of linear systems geometrically. All right, so I've got a linear system up here. I want to write out the associated homogeneous system as a matrix equation. So every system of equations has an associated homogeneous system. How are they related? What do I do to get the associated homogeneous system? Well, what makes a system homogeneous? 0, the equals 0. The right-hand side of all the equations has to be 0. So every system has an associated homogeneous system where you just take the right-hand side and make them all zeros. Okay. So that's what we're going to do first. I want to write this as a matrix equation. So we start with the coefficient matrix. So I have 1, 0, 2. Those are the coefficients on x1. Coefficients on x2 are 4, 0, 8. Then x3, we have -2, 3, -4. And x4, I have -3, -3, 6. So that's my coefficient matrix. Next, I have a vector of unknowns. My vector of unknowns should be x1, x2, x3, x4. Yep, thank you. And that should equal your vector of the right-hand side of the equation. And since we're dealing with the homogeneous system, the associated homogeneous, that should be zeros. How many should I have in there? 3 by 1, yeah. 0, 0, 0. So just to remind you, the dimensions on this coefficient matrix is 3 by 4, 3 rows, 4 columns. So the vector that I multiply has to be 4 by 1. The inner dimensions have to match. So this is 4 by 1. And then the result should be the outer dimensions, the 3 by 1. How would you solve that system? The augmented matrix. Yeah. Create an augmented matrix and row reduce. Yep. That's pretty much how we solve everything. So we're going to do the augmented matrix. 1, 0, 2, 4, 0, 8, -2, 3, -4, -3, -3, -6, augmented with the 0, 0, 0, and row reduce. So finally, I've made you do a bunch of problems where you have to row reduce by hand. I'm going to trust that you all know how to do it by now and know how it works. And I'm going to show you how to do it using technology. Okay, so on your TI, there is a matrix button. It's either a second function or it might be its own button, depending on what version you have. But it should say matrix. So for me, it's a second function, so I hit second matrix. I'm going to edit matrix A. So I cursor over to edit, choose A, and then the first thing it asks for, what are the dimensions of the matrix you want to input? So this matrix I'm putting in here is 3 rows by 5 columns. And then we just enter as we go across. So we have 1, 4, -2, -3, 0. And then 0, 0, 3, -3, 0, 2, 8, -4, -6, 0. So we've got it all inputted. And then I'm just going to press the matrix button again, second matrix. This time I want to do some math on the matrix I just entered. So cursor over to math. And if you scroll down, you'll find RREF. Option B, RREF. So you hit enter for option B. And then it's asking what matrix do you want to RREF? And we have to tell it matrix A. So you go back into your matrix menu. And now we're just in the names column. Choose matrix A. Just enter. And it says, okay, I'm going to RREF matrix A. I did something wrong. Yeah. Yes. You just press enter on option 1. Oh, okay. Yeah. So RREF. And then you go back into your matrix menu and you choose enter for matrix A. And it gives you RREF. I'm just going to paste this into my All right, so that's the row reduced version of the matrix we just came up with. Saves us a lot of time, right? Wolfram Alpha can do this also. So if you're at home and you have access to a computer, you can do it there. Sure, Mathematica and MATLAB can do it too. So where are my pivot positions? The 1 and the 1, yeah, so here we go. So pivot positions correspond to basic variables. So what are my basic variables here? X1 and X3. So let's see, basic X1 and X3. And then free are the columns that correspond to non-pivot variables, which would be X2 and X4. So what does this tell us? Is this a consistent system? Yeah, it has solutions, has a solution. In fact, it has infinite solutions because we have free variables. All right, so if I want to write the general solution in parametric vector form, first I'm just going to write it in the form that we've been using in a previous class. So my solution is going to look like x1, x2, x3, x4. Okay, my column of unknowns equals my free variables. You just write free, right? So I'm going to have x2 is free and x4 is free. And then your basic variables you write in terms of the free variables. So I'm going to go back up to what I have written over here and change it to equations. So I have x1 plus 4x2 minus 5x4 equals 0. And x3 minus x4 equals 0. If you translate that our REF to equations, that's what we get. So x1, if I want to solve it in terms of free variables, just solve this guy for x1, I have negative 4x2 plus 5x4. And then x3, solve in terms of the free variable x4, and x3 equals x4. So I put x4 here. So this is what we've done before. Just identify the free variables, solve for the basic variables in terms of the free. Now I'm going to translate this to what we call parametric vector form. So the reason that we call it parametric is because we're going to use the free variables as parameters. Okay, so we're going to factor out the free variables. And then we're going to leave a vector of coefficients. Okay, so I'm going to rewrite this as a vector times x2 plus another vector times x4. So I'm factoring out the two free variables. All right, so to create negative 4x2 plus 5x4, I need to have a negative 4 here and a 5 here. Does everybody see that? Okay, so in my free position, my x2 is free. So what I'm going to do here is I'm going to put a 1 in the x2 column and a 0 in the x4 column. So instead of writing free, you just write x2. All right, so then in my x3 position, I have an x4. So I have no x2s and one x4. And then in my x4 position, that's free, so I have no x2s and a single x4. So that's called parametric vector form. Parametric because we used the free variables as parameters, vector because we have vectors in our answer.
Can you explain again
For the free. Okay, yeah. So in the x2 position, x2 is free, right? So instead of writing the word free, like, we're just going to write an x2. And instead of saying x4 is free, we're just writing x4. It's itself, yeah. It's whatever you choose it to be, yeah. All right, so I'm going to take each of my free variables to be 1. Okay, so I have two free variables, x2 and x4. If I pick them both to be 1, that will determine what my x1 and x3 are, my basics. And I'm going to come up with a particular solution. Okay, so x1, x2, x3, x4. I want a particular solution, and I'm going to choose my free variables to be 1. So I have negative 4, 1, 0, 0 times 1 plus 5, 0, 1, 1 times 1. Pick the free variables to be 1, and that will tell you, then you'll have all the variables. So this comes out to 1, 1, 1, 1. That should solve the associated homogeneous system, right? That should solve the system. And we can do a quick check. So my original equation was x1 plus 4x2 minus 2x3 minus 3x4, and it was equal 6, but this is a solution to the homogeneous system, so I put equal 0. And then if I plug in 1, 1, 1, 1 for x1, x2, x3, x4, this equation should be true, right? So we have 1 plus 4 minus 2 minus 3. Does that equal 0? Yeah. And then you could check the other 3 equations too. It'll work, I promise. So verbally, I want to describe this set of solutions This is all of my solutions. There are infinite solutions. I've described them here. I want to describe the set of solutions geometrically. So where do these solutions live? R what? R4, yeah, because those are vectors with 4 entries. They live in R4. Okay, so they live in R4. Is it all of R4? No. So R2, what you're saying is it's two-dimensional, right? It's not all of R2, but the solutions are two-dimensional because there are 2 free variables. Yeah. Okay, so it's a plane within R4. So it lives in R4, which we can't picture, but it's a plane in R4. That contains these 2 vectors and the 0 vector. So a plane within R4. Here's a little quirk of your textbook. If the solution had been 3-dimensional, like there were 3 free variables, they still call that a plane. Right? Even though it's some 3-dimensional object within R4, they still call it a plane because we don't really have a word for a 3-dimensional object within R4. So they're just sort of expanding the definition of the word plane. So you can always use the word plane when it's some subset of the space. All right, so that's it for the lecture for class 5. You can start the activities, and I'll stop you with a little bit of time left to start class 7.